Hello once again. Let's look at molecular diffusion in liquids. So you'd find that solid diffusion in liquids is a rate determining step in numerous industrial processes where mass must cross a liquid interface. So the key characteristics are that we have a low diffusivity, typically 10 to the power minus 9 meters squared per second, indicating something that is a rate that is much slower than in gases due to high molecular density. Then viscosity dependence, you would find that with liquids, as you increase the temperature, the fluid becomes thin, or its viscosity is reduced, whilst when the temperature is also reduced, its viscosity increases, making it thicker. So major industrial applications, your liquid extraction there, and then a good example is that one where we look at the recovery of penicillin from a fermentation broth. Then gas absorption, a gaseous solid dissolves and diffuses into a liquid adsorbent, and our CO2 removal from flue gas, a typical example there, making use of amine solutions. Then distillation, a transfer of the mass between the rising vapor and falling liquid on a tray there. And a typical example is the one we look at, separation of ethanol from water or crude oil refining. So a comparison there of the diffusion in environments that we can look at is, so the phases that we are looking at is, number one, we are looking at our gas, which will obviously exhibit low resistance as there, due to our particles having free movement. But then when you look at the liquid indicated there, you would find that the resistance has increased. That's why now we can talk about diffusivity that is much slower as compared to the gas. And if we move further to our solid there, you would find that they are even much slower. The diffusivity. That's due to the closeness or close packing that is found in the solid, meaning that the resistance is very much high there. So as already explained there, so the diffusion in liquids is much slower than in gases due to, number one, molecular proximity there. There is crowdedness. That crowdedness results in frequent collisions, and hence that affects the movement. So as a result, these constant collisions act as a barrier, slowing down movement. So the net movement in a particular direction is resultantly slower. So when we want to model liquid diffusion, whereby we want to calculate the molecular flux in the liquids, one thing that is to be understood is that the kinetic theory in gases is much developed, but for when it comes to the uh, to the liquids, it's not yet fully developed there. So what do we do? Then it means we would approximate the mathematical blueprint that was used in gases for our um, liquid. But then there are key differences. One of them is your diffusivity is much slower there, and the effects of viscosity and pressure would also be handled differently. So two fundamentals model for liquid diffusion is the equimolar counter diffusion, there where the convectional term disappears there, because that is basically zero. The net flux there is basically zero. Then what's left it becomes identical to diffusivity only. Then we have the unimolecular diffusion. One component moves, then this movement creates a bulk wind that adds to the diffusivity transport of component A there. So a closer look at equimolar counter diffusion, as you can see there, as indicated there. We are looking at a scenario whereby we start with the general equation, and if you still remember, the general equation is Na is equal to, because we are now talking about liquids, we would talk mainly about X A as a standard there, then Na plus Nb. This is equal to your C. Now we talk about C average, then our DAB being equal to XA1 minus XA2, or in brackets. So all this will be over Z2 minus Z1, as you can see there. But then we remember that this term Na equals to minus Nb, so substituting there, either way, this whole term is reduced to 0. So we are only left with Na equals to Ca average, DAB. So rewriting that now is our Na equals to, so Na equal to C A average DAB brackets XA1 minus XA2 all over Z2 minus Z1. You would find that this is similar to the equation of JAB there. So, all right. So moving on. All right. So you'd find that this is the equation we get. Sorry about that. Here we have left CA average. How best can I do this? So this equation, needs to be corrected. It's CA average DAB brackets XA1 minus XA2 over Z2 minus Z1. So there we left CA average there. Right. Moving on, we now need to define CA average as a new term that came into that equation, and that CA average is your density divided by molecular mass. So your density component 1 divided by molecular mass component 1, which is M1 plus your density component 2 over your density component 2. Right. So you'd see that CAV is the average, your average total concentration. Average total concentration there. So moving on to unimolecular diffusion of A through non-diffusing B. So the most important cases of diffusion is that where solid A is diffusing and solvent B is stagnant or non-diffusing. An example of this is your propionic acid in a water solution being conducted with your toluene. Only the propionic acid diffuses through water phase to the boundary, then into the toluene. So the toluene water interface is a barrier to diffusion of your of B, which is water. So NB, so NB there, this is 0. And because of that, we then rewrite our equation is indicated there as follows. So we just replace the P over RT. We replace the P over RT with this, and we get equation as indicated there. So where our log mean is similar to as defined earlier, as and note that XA plus XB1 is equals to 1, and that can further be simplified as into that.